Hello, welcome to the first lecture of the Colloids and Surfaces section of Advanced Physical Chemistry. In this lecture, we're really just going to cover an introduction to the concepts of colloid and surface chemistry, why they matter, why they're different to bulk physical chemistry, and what you can learn by interrogating colloidal systems and interfacial surface systems. The objectives of this lecture are really just to define and understand colloidal materials, to explore the various classes of colloid as they're defined, to understand why colloids have very different properties to bulk materials, which is the main reason they're of interest to us, to understand how surface chemistry really controls how colloidal systems behave, and become familiar with key examples, particularly the model systems that we're going to further explore as the course progresses. So the most important and fundamental question for this part of the course is, what is a colloid? It may not be something that you've come across before, it may not be a term with which you're familiar. In very simple terms, a colloid is one material dispersed in another. Now, that comes with some caveats. It doesn't refer to all dispersed systems, but it does refer to a large variety of dispersed systems, and certainly materials that you've come into contact with this year, this week, even today. Colloids are really a group of materials characterized by a length scale rather than by any other chemical or physical property, and that length scale is typically nanometers to microns. So you can think of them as the materials or the concepts that bridge molecular chemistry and bulk properties. So instead of interrogating a molecular or atomic bond length scale, or interrogating a large sample that's macroscopic and visible with the naked eye, colloid chemistry looks in the intermediate space, where we have very finely divided materials that have very high surface areas and thus different properties to both simple molecular solutions or bulk systems. Now, the divided material in a colloid can come in many forms. It could be solid, so it could be things like solid particles, which you would find in paints, coatings, engine oils, powders, and in solid aerosols such as smoke. Or it could be something soft and deformable, so this could take the form of a gas bubble, an example being foam. Or it could take the form of a liquid droplet, which would give you generally an emulsion, or if it's a liquid droplet in air, an aerosol. Now, this isn't a complete definition of colloids, because we also encompass in that definition certain soft or squishy or deformable materials with length scales appropriate to the colloidal domain. So we also classify things like liquid crystals and some biological systems, such as blood, as being colloidal, because they have the properties as defined by a length scale. So if we take solid, liquid, and gas as the three most useful, for our purposes, forms of matter, then we can generate a matrix of different possible colloidal systems if we think about the continuous phase, being the phase in which the material is dispersed, and the dispersed phase, which is what has been broken into small particles or small parts. Now, interestingly, you can have a solid matrix as your continuous phase. Of course you can, when you think about it. And a classic example of this is solid foam, so polystyrene foam, packing peanuts, insulation, etc. Clearly, a liquid in solid dispersed system means you have a solid matrix encapsulating liquid particles. And a good example of a solid emulsion, which is what that's called, is butter or margarine, where you have liquid water droplets in a matrix of solid lipid or fat. You can even have a solid dispersed inside a solid, so small particles of that nanometer to micron length scale dispersed in a solid matrix, and a typical example of that is pearl or opal, and their remarkable optical properties arise from this very specific dispersion of a solid inside a solid with different properties. And as we liquefy or gasify the continuous phase, we get dispersions or colloidal systems of very different properties. So a solid dispersion in liquid is clearly dispersion of particles, such as you would find in paints and inks. A liquid in liquid dispersion is an emulsion. And a gas in liquid system is obviously a liquid foam, such as on the top of a carbonated beverage. Solid and gas systems and liquid and gas systems form aerosols, and a typical example of a solid aerosol is smoke, liquid aerosol clouds, or aerosolized personal care products such as deodorants or emulsifying sprays. Why can you not have a gas in gas colloidal system? Well, because of the properties of gas molecules, all gases are mutually immiscible, at least in thermodynamically resolved or eventual terms. So here are some typical examples, most of which we've talked about in the previous slide. Things like milk, blood, these are examples of colloidal systems that you come across relatively frequently. The television in the center represents a liquid crystal display because this is a colloidal material where you have a unique set of properties offered by the tectons that make up that liquid crystal. So colloid chemistry is significant because colloidal materials are finely dispersed and therefore have a very large surface area. And so as a little thought experiment, we're going to compare the properties of a gold sphere with radius 1 centimeter and a commensurate amount, so the same amount of gold broken into particles, very tiny colloidal particles of radius 10 nanometers, which are very easy to make in the lab. So we calculate the surface area of the gold before and after this process. So our original gold sphere, simple volumetric equation, gives us the volume and then by differentiation the surface area. And we can see that this gold sphere, which is the size of a medium to large marble, has a surface area of 12.6 square centimeters, so not very much. And looking at the density of gold, we can calculate the mass, and from the mass, we can calculate the value. And this tiny marble of gold would be worth over $3,000 because gold is a very valuable material. Now, if we take that marble of gold and break it down into particles of radius 10 nanometers, then by using volume and number density equations, we can very easily calculate that we have 1 by 10 to the 18 particles, each of radius 10 nanometers, and the surface area is now 1.3 by 10 to the 7 centimeters squared, or about 1,256 meters squared. That's 1.5 basketball courts. Now, you can imagine if you have a property or a system or a process that requires surface or interface, such as an absorption process or a catalysis process, then the properties of our gold marble versus our gold colloid, which is what we've made in the case of the small particles, are going to be very different. And so this is the beauty and the brilliance of colloidal systems, that this enormous surface area gives you vast access to be able to do processes at interfaces. And that's really what colloid chemistry and surface chemistry is all about. In order to understand why colloids are important, you need to understand surface chemistry. Now, in Australia, we're particularly beholden on colloidal systems. I've highlighted here just a few key Australian industries that use colloids as their core business. So in the mining industry and mineral processing, we have froth flotation, leaching and emulsion explosives, all of which are core colloidal systems and which the mining industry relies on in order to make their products and do their business. Agriculture, things like crop spraying, milk and dairy, water treatment, water use, all of those are colloidal processing systems. Manufacturing industries, energy, waste, healthcare, etc. So we can see that a vast proportion of Australia's economy really relies on colloidal systems, and given the examples earlier, that shouldn't really be a surprise to you. If you don't care about money, then colloids are very interesting from a fundamental perspective. Here we have a delta where the river in the southeast corner of Melbourne is meeting the sea, and you can see something quite interesting happening where the river water meets the salty seawater. Particles drop out and you have this silting effect. And this is because the salt changes the particle stability. We're going to talk about this a lot in a later lecture. But for now, just understand that colloid science can be applied to vast scale environmental questions, as well as small-scale catalysis questions or processing or manufacturing. And perhaps my favourite example of colloid science as an esoteric but equally important feature of the world around us is what happens when a bubble bursts at an interface. So a gas bubble rising through liquid, as you can see at the bottom here, when it reaches the interface, obviously it needs to break at the interface and be liberated into the external gas phase. But in doing so, it creates a jet, because this is a very energetic process. And that jet liberates a tiny droplet or a series of tiny droplets. Now, these tiny droplets from a glass of champagne or other carbonated beverage contribute strongly to the sensory perception of that drink. So these will evaporate quickly and leave scent molecules that contribute to the aroma of the drink and the way that aroma is delivered. In the ocean, these tiny droplets are obviously salt water, and so as they evaporate, they turn into tiny salt crystals. These tiny salt crystals are whipped up by the air into the medium atmosphere and diffract and scatter light there and contribute hugely to protecting the surface of the Earth from UV radiation. So you have this process to thank for the fact that we're not all cooked by the sun's radiation. One of my personal favourite colloidal systems, and something we'll talk about in the later lectures, is colloidal systems formed by surfactants. And so this is a rather unusual looking surfactant, but many surfactants have the properties of being able to form liquid crystals. So surfactants or detergent-like molecules are obviously widely used in cleaning and coating and emulsification and spreading, etc. But at high concentrations, they self-aggregate and orient to form these remarkable condensed phases that have the local order of crystals, but long-range lack of order. And so at long length scales, they behave like liquids, hence the name liquid crystal. So they have an extraordinary set of optical properties which are taken advantage of in the liquid crystal display, which no doubt you are watching this lecture upon. Surfactants, because of their unique set of interactions, can aggregate into a whole bunch of different structures, and in the final lectures of the course we'll see how those structures can be utilised in a range of applications. But just for now, take a look at the extraordinary library of morphologies that this picture represents a small selection of. A lot of colloid science can be summed up with very simple systems, which is rather beautiful and elegant. And one of my all-time favourites is the simple soap bubble. Now, this is different to the bubbles we talked about a moment ago, because this is a gas bubble surrounded by an extremely thin skin of liquid. So it's gas inside gas, protected by a thin skin of liquid, and surfactant absorbed at that liquid-air interface on both the inside and the outside of that membrane in order to stabilize it and allow it to exist. And this system is something that's fascinated colloid scientists for several hundred years, including some of the greatest minds who've ever lived. And you can see a list of them here. And many of them are Nobel Prize winners, and each has interrogated a specific part of this system to try and understand what allows it to exist and have this perfect symmetry and the beautiful iridescent colours that you see. The iridescent colours we understand very well now arise from the interference of light within the film, so light bouncing at the two interfaces, the inner and outer skin of the liquid film, interfere, and as lights of different wavelengths interferes constructively and destructively, you get these beautiful colours that you see as, for example, on oil slicks at the petrol station. What this really means is that the bubbles we produce, those beautiful soap bubbles in your washing up bowl, have film thicknesses that are on the same order of length as visible light. So we're talking some hundreds of nanometers to some microns, so an incredibly thin skin of liquid. Remarkable, and how surface chemistry controls this process and that skin of liquid is crucial to all wetting, spreading, and surfactant-based phenomena. And we're going to look at that later in the course. So, to finalise this lecture, I'm just going to sum up some important model systems that we're going to look at. And then they're very simple at first glance, but they're beguiling for that reason. They're also very complicated in an interesting set of ways. So, the simplest system we'll look at is a solid particle in a liquid. The liquid will probably be water, the solid particle will be something chemically simple, like gold or silica. We'll also look at oil droplets in water, gas bubbles in water, and solid surfaces in a liquid, probably water. Now, you'll notice one common theme here, that water is implicated in a lot of what we do. There's a reason for that. It's extremely ubiquitous. 2/3 of the Earth is covered with water. It's the most relevant and abundant liquid to human life. It's sometimes called a universal solvent, but equally we know that many things don't dissolve in water, and that fact is going to be increasingly important, and the energetic basis for what's going on there is going to be increasingly important. Water is also a very green solvent in the sense that although it takes a lot of energy to change its properties because it has a high heat capacity, it can be released into the atmosphere with impunity, and so the idea of replacing volatile organics with water is very appealing. It's got a very unique and unusual set of properties that really aren't predicted easily by a simple analysis of it. Most of these are related to its very strong hydrogen bonding capabilities. It also has a lower density as a solid, which is rather unusual and allows ice to float on water, which turns out again to be extremely important for life on Earth. So the secret to all colloidal systems, and I would go even further and say the secret to all of chemistry, is to understand what's happening at an energetic level. As much as one hates to resort to equations too easily, thermodynamics really does control all of chemistry, essentially, and ultimately all of life. Now, we won't use too many thermodynamic equations throughout this course. We will use equations, but not too many thermodynamic ones. What I think is more important is to develop a physical feel or a physical intuition for how physical systems are going to behave. And that's what I hope to provide you with over the course of the first few lectures, such that by the end of the course, you can have an almost innate understanding of what's likely to happen based on looking at the facts of the system, looking at the interfaces, the materials and their properties. You'll be able to divine what will occur in a given set of circumstances, such as dispersion or processing, or cooling or heating or evaporation. So for each phenomenon you come across, think, what's the energetic reason behind this behavior? There will be a balance of energy and entropy, and surface chemistry is deeply controlled by these things. So if you think of everything in terms of energy, it's always going to make sense. Okay, that's it for this lecture. In the next one, we're going to talk about fluid interfaces, and from there we'll move into soft and hard colloidal systems, so droplets, particles, and eventually surfactants and self-assembly. So that's a roadmap for where we're heading, and I look forward to speaking to you again soon.